Welcome to Laser Damage Live. We hope you enjoy this live footage of damage propagation.
This is our second video on laser-induced damage. Our first video showed material being ejected from the back of an optic by a high-power laser beam. This time, we'll show what happens when the optic is kept stationary in the beam. So optics damage when the laser intensity is above the damage threshold. At BRL, we always use a divergence beam, ensuring that the highest intensity is located at the front face. However, when a very intense beam passes through an optic, a nonlinear effect known as the Kerr effect can cause the beam to self-focus. As you can see in the diagram, this means that the beam can be smaller, or in other words, more intense, at the exit face. This can push the intensity to be above the damage threshold. Nonlinear effects, such as self-focusing, require very high beam intensities and a long path length. It's only because of the excellent coating that we can show this happening in fused silica. In fact, the coating has to increase the damage threshold by roughly 30% from the uncoated, polished substrate. With a worse coating, the optic would just damage at the front face and the Kerr effect would not be observed. In our first video, the optic is moved through the laser beam, hitting many different sites and ejecting material at each one. Here though, the optic is kept stationary. After the first pulse damages the rear face, each subsequent pulse hits an area that has already been damaged. Because the damage has changed the optical properties of the substrate, the laser can't pass through and is absorbed. Therefore, each pulse damages a section of substrate slightly closer to the front face, and you can see this propagating forwards.
Here is a high-quality picture of the damage you just witnessed. You can see along the line of propagation and the glass reflow as it was melted and reformed during the laser pulse bombardment. The coatings here were supplied by House School.